All right, hey guys, what's going on? So today we are going to be talking about a little bit more on path integrals. This is going to be the last video on path integrals. And the idea here is we sort of talked about quantum mechanics, and we talked about how paths near the minimal action path constructively interfere with each other. We're now going to talk about quantum field theory. We're going to put fields into the picture. We're going to see how they play a role. It's not going to be too math heavy, which is going to be nice. And then after that, we're going to talk about a few things on effective field theories, and then we'll be done officially with the whole book. This is like a 500-page book. This has been a big undertaking. I know there's been some ups and downs. There's been some time durations where I haven't posted anything. But I'm sort of starting to get into the game here and really putting more and more content out there because this is the kind of stuff I really enjoy doing. Anyways, again, if you like this kind of content, make sure to hit that like and subscribe button. Let's get into the material now. So we're talking now about path integrals in QFT. Specifically, we're going to be talking about field configurations and how they evolve according to our path integral formulation. So we're going to start off, again, in QFT, the probability amplitude is a field configuration, and we become interested in how fields evolve over time. So we're not talking about how states evolve over time. We're talking about how field configurations evolve over time. So recall that a state going from A to B, it looks something like this, right? So we have this time a field at A, right? So this is our field configuration at A at time 0, and our field configuration at B at time t at some space-time point. Again, space-time point is going to help us define exactly what A and B are, but these are two configurations. This is the initial and this is the final. Pictorially, we can understand this as A going to B, and this is we have a field configuration at point A, and we have a field configuration of B at this new space-time point. Okay, so the way we're going to go about doing this, if we want to recall a few things. So from a while back, we talked about how the field configuration, when it acts on a state, we'll actually we can go through the math here, right? So this is the definition of, this was our Klein-Gordon field equation. Our raising and lowering operators are the things that play on the state, right? So this guy here, this is the lowering operator. Well, you can't lower anything below the 0 state, right? Below the ground state. So that is driven to 0. And we have this, right? So the creation operator is going to act on the 0 state. And then we have to get us this, right? So this is a particle with momentum k. So this is what our creation operator gave us. One particle with momentum k. And then we have this factor out here. This factor out here, again, this is a sum over k, right? So we need these weighted exponential sums over k at some space-time point, right? So what we have going on here is our field configuration acting on some state, some particle state, giving us one particle of momentum k1 at some weight, a particle with momentum k2 at a different weight, all at this space-time point, right? So what the field configuration is doing is it's adding particles of different momentum adding particles of different momentum at a particular point in space-time, right? And then the particles, the states that have, in which K1 is, say, large, this exponential is going to make it so that that state is most likely to be there, or most likely to be the one that is going to be observed. So the state configuration is the object that acts on the vacuum to generate particles at different momentum. That's essentially what I said. So therefore, when we go from quantum mechanics to QFT, we're going from states, which we called QFT, to field configurations, which is phi of x and t. And these states here, again, the things that operate, the things that act on these states are things like our position operator or our momentum operator, and this is sort of the equations that we're dealing with in quantum mechanics. Whereas in quantum field theory, what we're dealing with is these are particles. These are actual particles, right? So the state that we have is a particle at a particular momentum, and these things are weighted by these exponential factors out here. So the states themselves are a little bit different, right? These states here describe configurations. These states here describe numbers of particles with particular momentums, and that's gonna get us into ideas behind many body physics and stuff like that, which is something that I want to go over also in a separate playlist. But anyways, if we continue with this logic that we used last time of a path, we can now think of different configurations along this path, right? So we apply an action at each point, but we can also apply configuration at each point. Since the space-time point drives the configuration, which drives the action. So at every space-time point, we have some sort of configuration of a field, and that which is going to be acting on the vacuum state, again, to give us numbers of particles at that particular point. And as time evolves, again, because this is a space-time point, as time evolves, our field also evolves. And as our field evolves, our action is also going to evolve. So these things are driving each other. The space-time point drives the field configuration. The field configuration drives the action. And the action is what defines our classical path, or the paths that deconstructively and constructively interfere with each other that we've talked about before. So this is the picture that I like to keep in mind when we're considering this type of, or when we have this sort of mindset of how can we make sense of an action, how can we make sense of field configurations, how can we make sense of path integrals, all in sort of one cohesive outlook. In this case, the space-time points drives the differences in the configurations for our operator fields. And that's the main point here, right? I'll reiterate it one more time. Space-time drives the field configuration. The field configuration drives the action. And that's how we go from quantum field theory to path integrals, and then from path integrals to classical field theories, right? So that is that, right? That is path integrals in a nutshell. We've done this in about 3 videos. We really only have like 2 videos left, I think. And after that, it will be symmetric physics. That's the playlist that I'm covering next, and I think you guys will enjoy that. So if you guys enjoy this type of content, make sure to hit that like and subscribe button, and I'll see you guys in the next one.